Week 3 focused on answering the questions, what is energy and how do we use it? In particular, we looked at the following concepts. What is energy and what is power, and how do they differ? How do we measure energy and power in different forms? How can we compare energy production and consumption from different sources? How do we use energy? How much energy do we use? What challenges are associated with trying to change a system that is based on a diverse set of energy production options and consumption trends? You watched a short video about hockey to explore the differences between three key terms: work, energy, and power. This video defined work as a force acting upon an object, resulting in the displacement of the object. In order to calculate work, you can multiply force times distance. What does this have to do with energy? Well, energy is defined as the ability to do work. In the example from the video, the amount of work the stick did was calculated as 154 joules. We can also say this is the energy applied by the stick. Energy and work are both measured in the same units, and for our purposes in this class are essentially the same thing. However, we will not usually be calculating energy as force times distance. We will be converting energy units from one form to another, or figuring out the amount of energy from the amount of power given. Power is the amount of work or energy done over time. In other words, power is the rate of energy transfer. To get power from energy, divide the amount of energy by the time it took to expend or use that energy. In the example from the video, energy was measured in joules and happened over a fraction of a second. So power is measured in joules per second, which is the same thing as watts. If you have ever changed or seen a light bulb, you are probably familiar with the term watts. However, like most people, you may have assumed that the number of watts in a light bulb signifies the amount of energy the light bulb has. Energy and power are often confused by people in conversation, in newspaper articles, and even in scientific articles. The watt is not a unit of energy, it is a unit of power. To convert from the watt to the equivalent unit of energy, you must multiply by time, since power is energy divided by time. When discussing electricity, we often will use hours as our unit of time. In that case, the amount of energy used by a light bulb will be measured in watt hours, or you may be more familiar with the term kilowatt hour for measuring energy. Remember, to convert from energy to power, divide energy by time. To convert from power to energy, multiply by time. And learn to recognize these common units of power and energy. The joule and the watt are the official international standard units, or SI units, of energy and power, respectively. However, in the United States, we tend to talk more about British thermal units, or BTUs, for energy, and kilowatts for power. In fact, you will often hear the term quad when energy is discussed in the United States. This term refers to energy measured in quadrillion British thermal units. The kilowatt hour is the standard unit of electricity measurement. During week 3, you also learned about the many different forms of energy. Energy can be found in motion, sound, chemicals, objects, heat, and many other places. However, the most important forms of energy that we will be discussing are kinetic energy, the energy of movement; potential energy, the energy stored in an object; chemical energy, the energy stored in the bonds of atoms and molecules; electrical energy; and thermal energy, the energy in heat. These are the forms of energy that are the basis for most electricity, transportation, and heating options. There are also physical laws associated with converting from one form of energy to another. The first is the law of conservation of energy, that energy can neither be created nor destroyed, only converted from one form to another. The second law says that converting from one form of energy to another always involves the loss of usable energy. These two laws seem to contradict each other. How can we say that energy can't be destroyed and at the same time say it's always lost? Doesn't lost mean destroyed? Actually, in this case, lost means lost from a particular system, not lost entirely. For example, we will be discussing energy losses in the electricity transmission system in Unit 2. But these losses don't mean that energy is actually lost forever or destroyed, just that it is lost from the system, converted to another form and allowed to escape. In the case of electricity transmission, this usually means that electrical energy was converted to heat energy, and the heat escaped to the atmosphere. We use different units of measurement to describe different forms of energy and power. For example, although the international standard unit of energy is the joule, you will most often hear oil energy measured in barrels, but a barrel can mean different things, as the examples shown here describe. How then do we compare the energy in a barrel of oil to the energy in a cubic foot of natural gas, a gallon of gasoline, or a ton of coal? Even more complicated, how do we compare the energy content of a primary energy source like oil, natural gas, or coal with that of a secondary energy source like electricity? To make any of these comparisons, we need to convert all energy amounts into common units first. In the US, the British thermal unit, or BTU, is usually the unit of choice. You can use tables like these, or calculators like the ones you explored in Week 3, to do these conversions. Comparing primary energy production from primary sources like coal and natural gas to energy consumption of secondary energy sources like electricity is a little more complicated, though. We will discuss how to do these calculations more in Unit 2, but for now just be aware of the difference between primary and secondary energy sources, and the fact that there is a difference between the amount of primary energy you start with and the electrical energy that you end up using. Primary energy is energy in the form that it is first accounted for in a statistical energy balance, before any transformation to secondary or tertiary forms of energy. For example, coal can be converted to synthetic gas, which can be converted to electricity. In this example, coal is primary energy, synthetic gas is secondary energy, and electricity is tertiary energy. Secondary energy sources are also referred to as energy carriers because they move energy in a usable form from one place to another. The two most well-known energy carriers are electricity and hydrogen. We get electricity and hydrogen from the conversion of primary sources of energy such as coal, nuclear, or solar energy. Primary energy sources are converted to secondary energy sources through conversion processes, which means you have to know which step in the conversion you are comparing when comparing energy units, because as the second law of energy tells us, there will be some energy lost from the system through any conversion process. For non-renewable energy sources, the main conversion process includes combustion in power plants, furnaces, and engines. Some renewable energy sources also go through these conversion processes, but others like wind, tides, and hydropower go through a simpler mechanical conversion process, while solar photovoltaics use a different type of chemical conversion through special panels. While we are on the subject of renewable energy, it is important to note that renewable energy is defined differently by different entities. So when you talk about renewable energy, be clear about which sources you include in your definition. Another thing to keep in mind when converting from one energy form to another is metric prefixes. As mentioned before, the kilowatt hour is the standard unit of electricity measurement, but you will also hear the terms megawatt hour, gigawatt hour, and terawatt hour, depending on the scale of electricity we are discussing. If you memorize this chart of metric prefixes, it will help to keep this all straight in your brain going forward. Here is the kilo prefix associated with kilowatt. As we go up the scale, the prefixes refer to larger quantities, so you must divide by 1,000 to convert from one quantity lower on the scale to a quantity higher on the scale. So 1 megawatt hour equals 1,000 kilowatt hours. As you go down the scale, you must multiply by 1,000 for each step down. For example, there are 1,000 gigawatt hours in 1 terawatt hour. You may also see the symbol PWH, which refers to petawatt hour. This would be at the top of the chart above terawatt hour. So there are 1,000 terawatt hours in 1 petawatt hour. Another thing to keep in mind about energy units is the confusion surrounding the BTU. We don't often talk about just BTUs. We usually talk about million BTUs or quadrillion BTUs, as mentioned before. When discussing million BTUs, there is a lot of confusion about how it is written. Most of the time you will see it written as MMBTU, which may not make sense at first. Why two M's? Well, the extra M comes from the Roman numeral M, meaning 1,000, So mm is a million because 1,000 times 1,000 equals a million. To be extra confusing, sometimes people write a million BTUs with only one m, and this is acceptable as well. Unfortunately, sometimes people actually mean 1,000 BTUs when they write MBTU. So if you see MMBTU, rest assured it means a million BTU. But if you see MBTU, look for some explanation of whether it is really a million or 1,000. If there is no explanation, it probably means a million, but you may want to find another source of data just in case. Another question we covered this week was, how do we use energy? Energy use can generally be divided into four main end-use sectors: residential, commercial, industrial, and transportation. In the U.S., the largest end-use customer is industrial, followed by transportation, then residential, and then commercial. Commercial refers to businesses, office buildings, hotels, restaurants, etc. Industrial refers to manufacturing facilities, factories, etc. The short video you watched gave you some more information about how we use energy in the U.S. We use about 100 quads, or quadrillion BTUs of energy, each year in the United States. This is a nice number for energy statistics, because we can easily break down energy use by percentages. So when you learn that the energy source we use the most in the U.S. is oil, and we use about 35 quads of it, you also know that about 35% of our total energy use comes from oil. You will learn more about these trends during week 4 as you explore the full energy systems for the United States, other countries and regions, and the world. Over time, total energy use has increased in each sector, and the relative proportions related to each end-use sector have remained similar. The exception has been during periods of recession or economic downturn, when energy use has dropped in all sectors because people can't afford it. The residential energy end-use sector is of particular importance in this course because it is the sector in which average citizens can make the most difference through adopting conservation, efficiency, and renewable energy options. On average, most of the energy in our homes goes to space heating, water heating, lighting, appliances, and gadgets. However, the total amount of energy used in homes and how it is distributed varies significantly by region. The Midwest and the Northeast regions need more energy for space heating, while the South and some parts of the West will require more energy for air conditioning, and not so much for space heating. Also, energy use in homes in these regions has changed over time as people have moved to warmer climates over the years. The way we use energy in our homes has changed over time too. Efficiency has improved greatly over time, but so too has the number of electronic gadgets we are using. So the overall result is an increase in energy use and a shift to a greater share of our home energy use being for gadgets rather than for heating and cooling. All of this information leads us to the last question. What challenges are associated with trying to change a system that is based on a diverse set of energy production options and consumption trends? Well, there are many challenges, too many to list here inclusively. But here are a few you may have thought of in your group discussions. First is confusion. As you learned about all of the different ways to describe and measure energy, it may have seemed a little overwhelming. It is confusing to people who study this for their job. So how are average citizens expected to be able to keep it all straight and make informed energy choices, especially when there are so many options? As we will see in Units 2 and 3, when you have so many options to choose from, it can be a challenge to figure out how to choose. Also, there is the classic conservation versus clean energy debate. Should we put our resources into promoting conservation and efficiency efforts, or replacing energy sources with cleaner ones, or both, recognizing, of course, that we have limited resources to expend on either? There are also challenges associated with changing energy in one sector, when those changes may have negative impacts in another sector. And the energy infrastructure we currently have has been built over more than 100 years. If new options require changes to this infrastructure, that can be a significant challenge. And of course, there are many more challenges that you have identified in your group discussions. We will be exploring these challenges more in the weeks to come. Now let's head into week 4 and start learning more about where we are currently getting our energy from.